Today on the RH podcast on AI, we have Dr. Somdeb Majumdar. He's the director of AI Labs, a research organization within Intel Labs.
My advice would be, if you're a high school student or in that sort of period, just do math, linear algebra, matrices. It's funny, my high school teacher back in, I think, 10th grade actually told me, I used to ask this question, like, why am I doing all this mathematics stuff? Where am I going to use it in my life? And she said, I still remember, there's a true story. She said, the one thing you should take away is matrices.
How's it going? We started recording now,
Pretty
by
good.
the way.
Okay.
Pretty
all right.
good? Yeah.
Yeah.
I wanted to talk, there's so much to talk about for what the things that you do. I'm super, super interested. So it's hard to know where to start, but I just would love to for you to talk a little bit about Intel Labs and what you guys do. Just go.
Yeah, so Intel Labs is, I would say, quite a special place in the middle of a gigantic company. Intel, as you know, is 100,000 plus employees. It's a design and manufacturing company, one of the stalwarts of computer architecture, starting from the days of x86 to all the way to today, where we have a plethora of heterogeneous hardware products. Labs is a very interesting place. It's a few hundred researchers that are tasked with finding sort of the next wave of technology. Obviously, AI is a big part of it. Many teams work on things that are not maybe traditionally AI, circuit design, software, and things like that. But there's no denying that AI has pretty much perforated and sort of made its presence felt in each and every division within Intel Labs. My group within Labs is AI specific. So I run a research lab called AI Lab, where we focus on algorithmic developments, looking beyond into the next 2 to 5 years to see what kind of new techniques and technologies need to be developed to address the sort of up and coming needs of the community.
Okay, got it. So, and when did you start with specifically AI Labs? When did you start running that?
I started, I think, this November, out of 3 years of running the lab. But I've been in Intel. Yeah, thank you. I've been at Intel for about, I want to say, 6 or 7 years now. So I've sort of seen the transition between different divisions and things like that. But right now, it's great to be in Intel Labs because it's truly a research organization, and we can, all be aligned on the expectations from our lab.
What do you think was the most sort of interesting thing you had to learn when running a lab? Because I would assume you had experience running things before, and when we're talking about running things for the sake of completing something on the business side, there's, I would say, quite a clear set of goals. But with a research lab, how do you think about expectations and goal setting and leadership?
That's a great question. I think the first lesson I learned is that being a researcher and running a research lab are two completely different things. I sort of went through the transition of being a researcher myself. Like, I've been in corporate research for the entirety of my career. But I've mostly been, for the vast majority of it, I've been, an individual contributor where I've built things, where I've developed solutions and so on and so forth. Led a few small teams here and there. I think when I had to take over the lab, I had to take on a whole different set of dimensions, mainly people that I didn't have to deal with. And with that comes a lot of complexities in terms of expectations. I think researchers are a very different breed. I think a lot of them come from a very open mindset, and they expect to see that kind of open mindset in the corporate sort of arena where they're working. And I think the biggest challenge, and almost a challenge I enjoy, is sort of steering through that balance of where do you make it, the lab relevant for the company, because at the end of the day, this is not a university, but at the same time, keep things interesting, intellectually stimulating for the people who work in it.
Right. So where have you found that line? I mean, what's your ethos on making, on drawing that line?
So my ethos is that, so I start from the point where I make the assumption that you can do a lot of types of research. Obviously, the type of research you would conduct at a university would be something that would take 5 to 6 years. Clearly, that would not stick in a corporate environment because no one's going to support you for this long. So what I've realized is the job of a research director or a lab director is to pick those problems and really sort of, position the problem out and sort of scope it out to maybe a year-ish out, which is about, as I think, the right amount of time to give people the breadth to innovate, but not get caught up in sort of the product cycles. But I think the effectiveness of a lab leader is to really see where does this thing land in about a year, and is there a path to transfer the technology to some team within the company or in the open source ecosystem where maybe developers and other researchers find it helpful. So that way we can pick those specific subset of problems that are still open-ended, that still don't have solutions, that have a lot of questions around efficiency, functionality associated with them. But again, it's back to the director's job to really make that connection that, okay, you can work on this problem for a year, but I know where this is heading and how this will exit into something the company cares for, or like I said, the developer community.
So let's talk a little bit about AI technology, which I think that's the primary concern of your lab. A lot of things have happened recently, but the LLMs, which is sort of language models, what ChatGPT is, and how people sort of interact with AI is primarily through ChatGPT. So this very human language friendly interface. So that's been really impressive. So I'd love to get your initial thoughts on that technology and how you see it affecting the market or companies in general, and us, and specifically also from a researcher's point of view, because you would have seen all the building blocks coming up that pipeline. You would have seen that first, and so it'd be great to hear your 2-3 cents on it.
Yeah, sure. So my take on GPT and ChatGPT will probably be very, very different from most even users of the technology or people who have sort of the business use for it. I think ChatGPT is great. It got, the whole world talking about AI, which means there's new attention on the area. It means people have started talking about where regulation makes sense, where regulation doesn't make sense. Questions about the responsibility or responsible AI has started coming up because obviously once the initial euphoria of writing cool dad jokes sort of went out of the, we went through that phase of, the honeymoon phase of ChatGPT. But now people are starting to use ChatGPT in actual enterprise applications, and people are starting to question the accuracy of the responses and things like that. So when you look at it from that perspective, I think it's great that it's brought the attention back to some of the most important questions around bias, around responsible AI, even around transparency, like how are these models trained, what data sets are they trained on. It's unlocked the whole Pandora's box of legal questions, as you might have seen in terms of the discussion between authors and content creators that are starting to talk to the point that their work might have been used. So I think from that perspective, it's fascinating to see this much, public interest in the field. I think go ahead.
So an interesting point that came up in my mind is, with regards to authors, this concept of authenticity of, I guess, creativity, I guess not necessarily thought in this case, because whether it's conscious or not is more of a fun exercise and an exercise that's fruitful. But as someone who has been playing with this for a while and understands it quite deeply, how valid is that concern that this is something that has been ingested from a human author? It gets the voice of the author, but it isn't the author. So what do you consider that a kind of plagiarism? Sort of like an abstract plagiarism in a way, because it will get the voice, right? So, or it may get the voice. So it's an interesting idea, but since you know the math, you know it a bit more deeply, what do you think,
So I haven't thought very deeply about this. I'm not a policy expert by any means. But I think the way I would think about the question of plagiarism, not just in, sort of this idea of provenance, is to think about it the same way we think about these concepts when humans produce output. For example, humans are language models. We have models inside our head that have been developed. Of course, there's a genetic mechanism that we are born with. We're predispositioned to understand certain concepts and things.
Which justifies the idea that it is a model, in effect, actually.
It is, yeah. I mean, it is a model. There's no question about it. Of course, we don't know the mechanics of it, but it is for sure a model. It's a black box model. And then it gets fine-tuned and you sort of learn based on various inputs. So what do we call things as plagiarism? Like, you could argue that everything we write is plagiarism because we've imbibe ideas and specific ways of expressing ourselves in literature, for example, by our experiences of ingesting books and poems and music and so on. But in the current world, we don't call that plagiarism. I think plagiarism is a very well-defined aspect of you're basically regurgitating what you've seen somewhere else without attribution to the source. So I feel like we should apply the same standard to machines. Regardless of what the training mechanism is. I don't think this is a technology question. I think it's a policy question in terms of thinking of it as a black box, just like we think of outputs from a human as coming from a black box, and apply the same standards to it.
Fair enough. So I have a question about your work. I'd love to hear some interesting things that you've come up with or you've stumbled upon on your research. Is there anything that really comes to mind?
I think one of the coolest things that come to mind, and of course this is super academic work, is back in the day, a few years ago, we were trying to build new types of learning algorithms. A new type of algorithm that we were looking at was in the context of reinforcement learning, which is a specific type of training, especially used in the field of robotics and things like that. And we were working on these benchmarks that involve, a team of players, virtual players, trying to learn a game from scratch, where they don't have any understanding of the rules, and they simply learn the rules of the game by, taking random actions, getting a reward from the environment, and then figuring it out as you. It's very human-like in nature, the way we learn things. This is also sort of the technology behind AlphaGo and AlphaZero, which you may have heard, that have come from. And I think, long story short, what blew my mind is some of the emergent behaviors, which almost spooked us. Because some of the, this was in the context of a soccer game, a virtual soccer game. And it was very interesting that the team that we were training, a team of virtual soccer players, eventually learned to coordinate with themselves, take all kinds of maybe moves that were maybe not beneficial to the individual player, but beneficial to the team. Even came up with team tactics like, the offside play, and sort of discovered these as they went. And I think that was sort of almost my moment where, oh, wow, this is, the AI is doing things that I don't know how the heck it's doing this. Like, I know I wrote the, sort of the training mechanism, but it's discovering all these emergent, properties and things like that. So I'd say that's one example among many where I've been sort of surprised by what these things can do.
So what was surprising about that in a way? Because maybe it's easier to say now than it used to be. But one thing we could probably say is like a lot of these features or a lot of these things you can talk about when we talk about any kind of rule-based space is that if you search the space long enough, you'll be able to figure out, every inch of that space. One of those inches would be the offside trap, for example. As long as you continue to churn the logic until it gets there, which is easy to say and hard to do. So I understand that. But so what was really surprising? Was it that it happened, or you didn't expect it to happen, or you didn't think it was possible that it could happen, based on your knowledge of basically the whole field?
Yeah, that's a great question. I think I would not have been surprised if it went down the road of figuring out these incredibly, complex strategies. I mean, offsite trap is a pretty complex strategy that I've been taking. But I would not have been surprised if this was truly written out in the traditional sort of rule-based, with using traditional rule-based algorithms, because in fact, I could go back and check where during the evolution of that sort of intelligent system, these kind of strategies began to emerge. I could relate it back to the specific rules of the game that I had encoded. I think what was surprising is that we did not do any of that explicitly. We essentially had a abstract representation of the system, which is, what are the actions you can take, you can pass, you can dribble and things like that, and just let it run. And what was more, I think, surprising is if you knew the technology under the hood, these are doing linear algebra. Forget rule-based systems. These are, matrices that are transforming data from one domain to what we call sort of this abstract embedding domain. And then you're taking all kinds of decisions and learning about the environment and about the sort of what is good, what is bad. But what's really happening under the hood are a bunch of tricks multiplications. And I did not think matrices had the power to, get a system to behave intelligently and to the point where it did not need to have explicitly encoded rules, explicitly encoded, sort of if-then-else statements to decide, how to take a particular move. So this was truly fascinating to see that, deep learning really worked. I mean, this was obviously a deep reinforcement learning, implementation.
I know we also talked, earlier about a project I thought that was really cool with proteins that you worked on in your lab. Could you expand on that a little bit?
Yeah. So I think maybe to think about how we think about proteins and things like that, there's a very interesting connection back to GPT and sort of not just GPT, but language ones in general. So I think when, researchers like ourselves look at a technology like GPT, we don't think necessarily language, even though the largest use case of something like GPT is language. We really see, and in fact, the T in that GPT, which is a transformer model, really the goal and the function of the transformer model is to make correlations between different parts of a sequence. That's the way to think of it. So a language or a sentence is made up of a sequence of words. A longer text is made up of a sequence of sentences, and it can go through the whole hierarchy of a particular textual sort of representation of logic, right? And what the transformer in that GPT is doing is really creating these internal models of what any point in the sequence, like a word in the case of a text representation, how it correlates with all the other tokens or all the other words in this particular case in that piece of text. But you could sort of abstract this out and say it's not just about text or things like that. Anything that is sequential in nature, and has a function that depends on these sort of correlations between different parts of the sequence, could benefit from this kind of sequence representation technology like the transformer. So this is where applications in science, for example, protein design or drug discovery, for example, or discovering new types of molecules, really comes into the picture. Proteins are very interesting. All proteins are actually made up of 20 amino acids. So you can think of a protein structure as made up of usually anywhere from 100 to thousands of blocks, or let's call it tokens for now, because everyone knows tokens. But each token is really one of 20 possible types. So that's it. So think of it as a dictionary that has 20 letters, and you're trying to create sort of this long text material that is maybe 1,000 words long, but there's only 20 words to pick from. And so if you think from that perspective, it's very similar to a text type, text-based task. In text, it has various kinds of function. Maybe it's trying to sort of represent a particular emotion. It's trying to describe a certain situation. It has all kinds of sort of, functions associated with what the text represents. Proteins have a different type of function. Their function might be a particular sequence of these tokens might represent very specific properties of the protein. So this might be a specific drug that needs to dock onto another molecule or a sort of a target protein. And this sequence of amino acids sort of determines. And so the problem that we were working on and actually continue to work on is develop what we call language models for proteins. And so we call these protein language models. And try to create these language representation proteins. So you can do all sorts of things with it. You can generate new proteins, you can classify proteins, you can do all kinds of analytics on proteins. And again, why proteins? Because proteins are at the heart of drugs. They're at the heart of many biological sort of questions that exactly where life sciences, for example, is very important.
And this analogy of 20 letters to the space of all proteins is perfect for the problem. It's the perfect nail for your hammer, or it's very good nail for your hammer. It is. Yeah.
In fact, you would be surprised how many nails this GPT hammer has found, because even, there's an interesting, I joke that in the early days, by the way, early days is 10 years ago in AI. A lot of the advances in research was driven by computer vision. Like most of the solutions started with ImageNet, for example, where people were trying to classify cats versus dogs and things like that. And it's quite interesting that, yeah, exactly, that's right. Or the dress question: is it blue or is it gray? But then over the years, what has happened, and in fact, in the last couple of years, especially with the rise of transformers and these kind of, sort of building blocks of AI systems of today, NLP, or natural language processing, or natural language understanding, the field of language has driven a lot of the, underlying technology. But we see parallels, again, back to computer vision. There are these things that are called vision transformers, for example, which treat an image as a language. Like you could actually take sequences of pixels, and you could say, the pixels that represent this dog on the top left of this image has a certain relationship with the pixels that represent the person that's holding onto the dog. And you can make all kinds of, contextual understanding of an image, but based on this technology that came from language. So I think that's really the fascinating part of this field, where you can sort of take solutions that came from a domain and apply it to something that's completely different.
Yeah, I think, it seems like the best way to sort of treat this is to, whatever your problem set is, take this space, turn it into some sort of encoding, and make it as Godelian as possible, in a way, in terms of like, you have a bunch of symbols that you can shunt around with operators of some sort, and then it seems, which kind of makes sense because it is a computer, and then you have, you have the AI system infer the relationships between the structures based on some feedback on results, and it seems, and then we have all these tools to make that happen, and transformers being one of them, or structures to make that happen, and transformers being one of them. I want to soften it a bit and talk a little bit about you and how you got into all this in the first place, how you got into AI. I know you really actually started off in a way in a space that really makes sense, which is signal processing. So could you talk about that and how you got in, how you were, tricked into playing in this space?
I was supremely lucky to be at the right place at the right time, and thankfully with the right skill set to make the transition. Even it's funny, I run AI Lab, but I had no formal sort of graduate level training in AI. My Ph.D. involved signal processing, like you mentioned, control theory, operator theory, which is a specific field of mathematics. And I spent a long time developing systems that, were, and these are based on, sort of signal processing and things like that, or what we call codecs. In the area of low power systems. So we would build these, representation systems that went into everything from body worn, like, these headsets that we were, in fact, several years ago, we were building solutions for extremely low power headphones, which then went into a slightly different field. We started developing prototypes for body worn sensors for biomedical use cases and fitness use cases. So I think that part of my training and career really grounded me into thinking of technology in very rigorous terms. Rigor is a very important part of these traditional, fields like signal processing or control theory, compared to today's AI. Like things have to be almost closed form in nature in terms of the solutions that we are talking about. They have to be analytical, they have to be debuggable. So there's a lot more rigor involved in a lot of these classical engineering fields. And I'm really glad I went through that because right around, I want to say 2012 or 2013, it led to a point in my career where I understood the sort of strengths and weaknesses of these traditions. Strength, obviously, like I said, is the closed form nature of these solutions. It's very analytical nature and things like that. But this also was sort of its weakness because a lot of the closed formness of the solution or the sort of analytical ability, the ability to analyze the solutions really came from the fact that humans designed these solutions. For example, humans designed filters in signal processing, or wavelets, for example, were a big deal back in the days. But humans went and thought, oh, I need to, let's say image processing. I need to look at an image and I need to figure out where the edges are. Like I need to disambiguate between the boundary of a person and the boundary of a cat. Today we can do it with deep learning, but back in the day, people, spent PhDs designing these filters that would do that job for you.
It's the idea that people are spending their PhDs deciding where the line is between cat and human is.
It is. I mean, it took that much time because these are not because computers don't see images the way humans do. So it takes a leap of flight to sort of treat like you say, encodings of pixels and trying to figure out what we can do with those encodings of pixels to make it the machine work like the human. So it was a big deal. Before 2012, 2011, 2012. But we also found that this was also the weakness because there's only so much you can sort of plan for when you're designing these filters and things like that. And that's why I got into AI, because deep learning was taking off right around that time. The fact that I could build a deep learning system that could do classification on 1,000 class data set like ImageNet, which is very familiar, sort of a very important data set in AI, where you're trying to sort of classify between cats, dogs, and obviously much more than that. There's thousands of these, 1,000 of these different classes. Without knowing anything about image representation, blew my mind, because now a random person could come literally off the streets and I think in 2013, the ImageNet paper significantly improved the state of the art in terms of this classification accuracy on the standard data. And that blew people mind because these guys were not traditional computer vision scientists. They had not done their PhDs on how to design these printers, and suddenly they were beating all of the existing methods. And that's where I was like, okay, I got to shift. I got to understand how this whole deep learning technology works. And I think that changed my career trajectory for the better.
So a theme that has emerged from sort of having this conversation is this idea of a specialized skill set or a specialized space of understanding, or interacting with a language model to some degree, which may not be an ubiquitous structure, but is something, when we talked about chip design, I'm assuming that interaction, because it's not popular or because it works, but I'm assuming that interaction is also going to be most friendly through a language model where you're communicating in human language or something analogous to it, because language models, they even write code, right? So it's really just, can you have something alphanumeric emitted that makes sense? So I'd love to hear what you think about sort of, or how you think about that, right? Because what's the underlying idea behind having a language model, having a special space of expertise, putting all that together and to make something that's useful for people. So your example first was the protein, and the second one was sort of, I think more pertinent to Intel is chip design.
Yeah, so I think researchers tend to think of the representation problem. I think the AI research, we tend to think of, okay, we have, even language, right? We have sentences, words. Machines don't see words or sentences. So you have to have some kind of encoding. You refer to that. So how do we build an encoding? First, question number one. Back in the day, you could just define the encoding. You could define like a hash table. You could do all kinds of things with probabilistic encoding and things like that. But that wasn't very useful because you couldn't derive relationships between differently encoded data, right? So even language models went through this period of really figuring out how do you learn to generate new encodings. So the machine has to, you train the machine to come up with newer and newer embeddings, which are numerical in nature. But at the heart of it, you have to turn these non-numerical data structures into something that is a numerical encoding, fundamentally that is hopefully trainable, and then you can do interesting stuff with those encodings. In fact, in the AI world, we call those encodings embeddings, like you might hear this term, or not. But the whole representation game is to see how we can train the machine to come up with better embeddings. So it's the same thing when we think about proteins, or we think about things like chip design, where we ask this question again, and it goes back to what's the right representation policy for the data. For something like chips, or something like constructing a logic out of logic gates, the data structure might be very different. For example, one of the data structures we work with a lot are graph data structures. Graphs are obviously ubiquitous. You find graphs in social networks. Facebook or Meta, for example, would have a graph that represents people and their relationships between them. And something like Amazon might have a graph that is a product recommendation graph, where there are objects that people buy, there are people, and there are edges between, or connections between these nodes, people, objects, etc., that determine some kind of a relationship between them. On a circuit board, you have something similar. You might have nodes in you can represent it as a graph, where the nodes would be the components of the circuit. This could be, for example, the memory block, the CPU block, etc. Or you can go inside one of these blocks and go all the way deep down to the logic gates, right? But they all are connected, like literally, with wires, and sort of the sequence of connections means something. It's a function. And it means a lot of things other than the function. It can how you wire these things up can determine power. It can determine whether you're meeting timing, all of these specific technical KPIs for that system. So we tend to think of these things as, well, there's a way to represent it as maybe language data. In the case of the protein sequence, it makes sense because it's a sequential thing, and it's very akin to like a sentence or a string of words. On something like solving problems for, let's say, product recommendation systems, like if I'm on Amazon and I'm trying to add a new product comes into the sphere, and I'm trying to make a decision on should I recommend to Chris to buy that, dog collar. So that is a new decision that I have to make, and this connection doesn't exist because the connection between Chris and the dog collar, this particular object, doesn't exist because this dog collar is a new item. So it's an interesting prediction task where you're trying to predict on a new, relationship. So for a problem like that, or for a problem like saying, how do I arrange the components of my chip, I will go with a different representation. I might go with a graph representation. And then I have to, if I take the decision, I have to build out my entire stack of what we call graph neural networks, which is similar in spirit, but very different in implementation, that I need to build on top of these kind of new data. So we constantly have to take these kind of decisions in terms of what's the right way to represent the data. Once we've taken the decision on representing the data, what's the right sort of machine learning stack to put on top of it, which is really asking the question in plain speak, what is the right machine learning stack to convert this raw data to something that is compact, that is, that you can do, perform things like classification or prediction or any of these different tasks. So that's literally the life in the day of a researcher. We take these decisions day in and day out. We look at new types of data. We come up with new types of representation structures, and then training methodologies, and rinse and repeat.
Got it. So are there any algorithms or architectures that are really interesting to you right now that are really working for you?
So I think the big... technology, or I would say sort of, we call it primitives, like in terms of sort of the building block of this technology is clearly the transformer. A transformer is basically the core block that drives GPT or any sort of language model these days. And I think researchers have figured out all kinds of ways to make this transformer more efficient. So that continues to be a core area of research. How do we make sure that you can aggregate context over longer and longer, tokens? I mean, this is a big, for example, what this really means on the ground level for for users is that, for example, can I summarize a very long piece of text, like a very long book, for example, because each word in that book is a token. And if I can aggregate context over very, very long tokens, then I can do things like summarize an entire book. So that continues to remain sort of an interesting area for us. We're spending quite a bit of time thinking about other, sort of primitives that are more memory efficient and compute efficient. I mentioned graphs. In fact,
But you would consider graphs a primitives? I thought you would consider a transformer a primitive.
no, graphs are not a primitive. No, graphs are not a primitive. So I would consider graph as an alternative way of representing the data and building the primitives that would work on top of that data structure. Exactly. Yeah. So that means that we have to come up with efficient ways to do what are called these convolution operations, which are very commonly done on these computer vision inputs, for example. So we spend a lot of time thinking about that. We spend a lot of time thinking about how do we combine this idea of transformers and graphs, because graphs are fundamentally sparse in nature. Like the example I gave where things are connected to other things, there could be a lot of things, but not everything is necessarily related to everything. So this is a very powerful representation feature where I can actually now, for example, there was a paper where the authors argued that a transformer is basically a graph.
That's what it sounds like to me. Yeah, because in my mind I was thinking if you can superimpose the whole, it has to be an optimization there. But if you superimpose the whole, if you superimpose the whole space onto a matrix where every location represents the existence of a subsection of the line, you can literally draw like a 1-1, right? And then it is a sparse space, but then you would have to reduce that because then that means the size of the matrix is the size of the space, which is ridiculous. But you know what I mean? But in many ways, that's a very rudimentary perspective, to be honest, because there's a lot of work.
No, that's actually, you pretty much hit the nail on the head. I think the concrete way for maybe the researchy folks would be to think of is take a sentence. The sun rises in the east, right? One way to represent this is to represent it as sort of a sequence of tokens. The sun rises in the east. And try to sort of create these attention heads, which is what the transformer does, to say, or maybe a slightly complex sentence. Maybe the sun rises in the east and it sets in the west. So the word it is really related to the word sun. And so what the transformer really does is create these attention, models that tell you, that eventually functionally tell you that, these things like the sun is related to the word it in this sentence. So if you can query where does it set, then the response could be it sets in the west, or the sun sets in the west, because the model now has an understanding that it and sun are related. Now you can see where the graph idea comes right away, because you could also say, alternatively, in an alternative universe, you could say the sun rises in the east are all nodes on a graph, and they're connected with some kind of edges, and the edges might be representing sort of the correlation between. And so in this particular scenario, the connection between sun and it would be a very strong connection. And there might be no connection between, generic words like the, because the is not very useful discriminator. But you can explicitly build these graphs that are very, very sparse. And what that means for the execution of these, workloads on the hardware, on the GPU or the CPU, is that you're dealing with lower memory because there's fewer things to represent. You're dealing with fewer computation because there's fewer number of weights to update in the corresponding neural network that sits on top of this graph. So the graph neural network is correspondingly benefiting from the sparse nature of the graph that's lying underneath. So we play around with a lot, and this is a very active area in our research lab right now. Really go deep down into the representation space and see, is sort of this token-based, transformer-centric representation the right way to do it, or where is the world going towards in the next 2 to 5 years? And I strongly believe people will definitely come up with more efficient representation, and GPT will transform into something else. The T might become something else.
So how do we think? How does if you wanted to think about this from a chip design perspective, and I think it's a very unique perspective because, well, most people are thinking primarily on the software level and sort of almost, sort of at that tier. But on the chip level, you gave a great analogy. But how do you think about that? Okay, now we have this sort of sparse space, and this example is sort of graph-based as a fundamental representation. How does the chip take advantage of that, apart from the fact that it's sparse? Because you can make this argument that if it's sparse, so whatever abstraction representer that you have will take advantage, will be able to take advantage of that because it is just less data, and you have some sort of relationship-based thing that is metadata on your basic structure or something, right? So how does the chip itself, why does that excite you that the chip itself can take advantage of that? Is it because of something in the nature of the chips, or is it just in general that any sort of win on the chip level cascades to order of magnitudes up because it is the chip? Does that make sense? I wish I could ask that better.
No, I think I get the gist of the question. I'll try to, I'll try to sort of maybe explain it in a slightly more understandable. So so the first thing to understand is the chip doesn't know it's sparse, or what sparsity is or things like that. So we're trying to fundamentally solve the designer's problem, where the designer is looking at this bag of logic gates and sort of CPU components and memory components and power components, and trying to basically arrange them literally on a rectangle to say, what is the smallest rectangle inside which I can pack these, millions of, things. Now you can look at it at different hierarchies. You can look at it at tens of millions of logic gates, or you can look at the hierarchy of, macro functions that are comprised of these gates. Or you could look at these at the level of a chip level sort of blocks. So for example, the memory block or the CPU. But it doesn't matter what hierarchy you look at it. The job of a designer, someone who's sitting at Intel or other semiconductor companies, design companies, is to really ask the question, how the heck do I pack all these things into the smallest space possible? And people would give their right arm for a 5% improvement in the area or the power profile of the design that they build, because of the scale of the product. Millions and millions of chips are sold. If you can get it, if you can get the size down, that means the device inside which it's sitting becomes smaller. If it's a cell phone, if it's a laptop, if it's your car, power consumption is a big deal. So people in this industry would, spend a lot of time thinking about even incremental improvements to either power, performance, area, all of these things. So we come into this picture, even though I work at Intel, I'm not a computer architect, I'm not a design engineer. I look at it from the perspective of, this looks to me like a bin packing problem. And a bin packing problem is a very, very classic machine learning, combinatorial optimization problem, where you're trying to ask the questions, what is the smallest bin inside which I can, pack a number of different, Lego blocks. So it's very similar. It's actually a geometric question. So now your question back to, graphs and sparsity and things like that. The reason why,
sounds like a two guys in a van problem,
It is a two guys in a van problem, actually. But you sort of get the picture. And so now you realize, because of the scale of the problem, sparsity of graphs really matter, because when you're dealing with tens of millions of, let's say logic gates, it does not make sense to start with a representation where I need to compute attention, for example, using a transformer-centric language over all 10 million tokens. That would not work very well. And I know that's not even necessary, because different parts of the chip are sort of, can be isolated. So you can solve this problem in a hierarchical fashion, where there's sort of these sparse connections between blocks, but there are dense connections within blocks. So I can sort of have this representation which has different density of connections depending on spatially where you're looking at that layer. So it very naturally falls into a representation that is graph representation, and then you can build all sorts of machine learning stack on it.
Right. That is actually really, the way you explained it was very good, and it's just very powerful. Just the idea of having it so that it reduces in power in terms of the requirements of power. Right now, all ML has to happen on very large systems, and anything that has any utility is happening on the largest possible system right now. So there's definitely a need for a reduction in the amount of power that this technology uses in order for it to continue to sort of climb down that, what would you call it? Sort of, I guess, the power gradient. I forget the name of the guy who every 18 months, the power of chips increases.
That was us. That's Moore's Law. That was one of our founders. So I mean, I don't know the guy, but
yeah, no, I think I asked the right person. I think I had the right person there. So, there's a lot in that direction. But one thing I did want to talk about before we finish this off is this idea of proprietary information and open source information, and sort of how that it is, I guess, when we have large organizations that are trying to have or trying to use this, and this sort of goes back to this idea of when we talked about earlier, is the voice of the person from an abstract point of view something that can be considered something that the person owns and owns in perpetuity, or is any derivative of it valid? Because I'm sort of, is it an emergent property of these set of words? Even if this set of the English language, if this person has a tendency towards them, is the voice that they speak in just an emergent property of having all these words? So there's a lot of questions. There's a lot of fun abstract questions you can ask about that. But when we come to company decision making, policy decision making, that becomes a bit of a complex thing, right? Or the concept of ownership is quite important. So how do you? So for someone who specifically generates new things, right, in a company setting, and then has to draw that line themselves between what is and isn't company theirs, in the sense that it's the company's theirs in the sense that it's owned by other people. So how do you, and then also other companies that want to use this, right, and they want to make their own stuff, or want to use, or have whether they're outsourcing AI pieces. A lot of companies, I'm sure big companies, want to use this technology, and the faster they use it, the better for the people who are making it. But they do have concerns over their information and what's theirs and what's others. So I'd love to know what you think about this, because you're the initial point of that, where you make the thing and then we decide, how we use it. But you are making the thing. So how do you think about that as you're making this happen?
Yeah, I mean, there's just so many layers to that question. I think, like I said, a lot of us researchers who work in the corporate world wear two hats. One is the hat of the open ecosystem researcher, and this is the hat that believes in open source, believes in publishing, and being very transparent about publications, all the way down to what data sets are used, what methodologies are used, how the comparison with different baselines is done, and even down to how compute intensive the solution is. Like, is it going to be sort of sustainable in terms of the computing? And I got to say, I've seen at Intel very, very strong emphasis on these questions early on. In fact, there's a whole group of people that think about responsible AI very, very deeply. And even though we are very open source friendly, I mean, I would say 80% plus of the things that we develop, we open source in my lab particularly, and many other labs within Intel labs that work on AI. We're very open source friendly, but that also means that we are very cognizant of the responsibility that comes with releasing something to the public. Open source already takes away a lot of the friction because you can really go inside the code. But we also are very careful about what data is used to train our machine learning models. We make it very transparent in terms of the sort of the compute requirements, the memory requirements, and such. There will always be a niche set of things that don't make sense to open source, because this might be very valuable company IP that is directly responsible for generating massive amounts of revenue and things like that, and we have to take that call sort of project by project. But I would say the vast majority of the things that we do is open source. You also have to think, I mean, there's another way of enabling the open ecosystem, which may not be open source, but sort of the GPT model, where you still provide APIs to, sort of do fine tuning for your corporate data and things like that. Again, there things are a little bit of a slippery slope because, transparency is a very important thing. And you're already seeing this, to the point of derivative works and things like that, the question that you asked. People are finding out secondhand that their data might have been scraped. They're finding out by generating text that looks exactly like the text that they've written. And that's how they're finding out that their data has been used. And so I think for going forward, products like GPT or derivatives of GPT or whatever comes in the future really need to be open, at least about the data sources that they've used. And because this directly means whether you pay a royalty at that level to an author or a creator, right? So that is extremely important according to me, and something that I'm glad that sort of GPT brought that attention back to, sort of data ownership. And there's of course model ownership, which is a whole different question, whether you make the model open source or you make the model closed source. But at the very least, I can understand, sort of a lot of companies desire to make the model closed source because you want to control revenue and things like that. But I feel there's a point where, things like data provenance is non-negotiable, because then you open up from the company's perspective, you open up yourself to legal risk. And from the consumer's perspective, you don't know where on the plagiarism spectrum the content that you're consuming, where that lies. You cannot even make a definitive decision about that if you didn't know what data was consumed to begin. So I think these are very, very important sort of policy questions that will, I'm sure, keep us busy for many, many years.
I asked this question for the people who just stumble upon, the podcast, or, sort of trying to figure out what they're going to do in their in their careers, and see something like this and think, okay, what if I wanted to be sort of in the position of a researcher, but in this very particular niche, but at Intel or any other company. So I think I'll ask a very rudimentary question, which is, what do you think the best way to get started in this field is now? Where do you think people should be really focusing on as they complete, their high school or trying maybe to get into their masters, sort of trying to get to that next tier of accreditation or interest?
That's a great question. Yeah, I think the answer depends on where in their career path or their academic path people are. I think if you're talking about students that are in maybe high school, or even sort of, these days I've seen blogs from 8th and 9th graders writing about deep learning. So I'm not surprised anymore that they're thinking, but it's great that they're thinking. So I think if you're at that level, where you're at high school level, I think math. Forget about the buzzwords. I think my biggest advice would be stop reading, social media posts on AI. Stop reading all the book, either the doom and gloom or the other end of the spectrum where this is the best thing since sliced bread. Tune that out. Because at the end of the day, the people who build these systems are fundamentally mathematicians, logicians, computer scientists. So I think the focus on the fundamental sciences and mathematics is what is going to drive this field forward. And this generation that are currently high schoolers or at that sort of high school to just graduating into college, that is the perfect time to put your head down and just do the math, so to speak. I think if you're sort of an early stage career person who's just maybe graduating from maybe a 4-year undergrad course or things like that, I would strongly suggest going into grad school, even if it's for a couple of years, and take a few courses and maybe even do a thesis on machine learning or AI projects. I think it keeps if you enter the corporate world right away as a corporate researcher, there are a lot more expectations from the industry to start producing products. And I think that takes away from the focus on really, developing the technical skills you need to solve this. So my advice would be, if you're a high school student or in that sort of period, just do math, linear algebra, matrices. It's funny, my high school teacher back in, I think, 10th grade actually told me, I used to ask this question, like, why am I doing all this mathematics stuff? Where am I going to use it in my life? And she said, I still remember, there's a true story. She said, the one thing you should take away is matrices. And I don't think she even knew what role matrices would play. And it literally pays my salary. So I don't know what the equivalent of matrices for today's kids are, but I would say, just do math. And then if you've gone through that rigorous training of mathematics in high school or first year undergrad, and then go into a deeper study into maybe a 2-year master's program, you are really set to be a solid, respected sort of researcher who can actually deep dive and sort of disambiguate between all these, flashy terms like LLMs and general intelligence, and take that out of your head. Just focus on them, because math's gonna move this field forward.
Well, if people wanted to move forward and to find you, where would they be able to do so?
Oh, just I'm not much of a social media person. I think I'm just on LinkedIn, so they can find me on LinkedIn, send me a message. Be happy to chat with anyone and carry on a conversation.
Well, thank you so much for being on the program and being on the podcast, and basically just like teaching us about what you do and all the research you're doing. I'm sure there's lots of interesting things that are going to come out of your lab, and I'm looking forward to every single one of those things. And just thank you for teaching us about how chips can be improved, and some of the protein stuff you're doing. I think those things are really, really cool and really, really interesting. And I'm looking forward to seeing them in the market as you're working towards.
Absolutely. Thank you, Chris. This was super fun for me.
Good. Thank you.